Hello everyone, I'm Jiatu from Tsinghua University, and this talk will discuss the unprovability of strong complexity lower bound in bounded arithmetic. And this is a joint work with Igor, Oliveira at the University of Warwick. Here's an overview of today's topic. First, we will give some background of the research problem, which is why we are interested in the unprovability of complexity lower bounds. Then we will discuss basic knowledge of bounded arithmetic and previous results on this topic. Then we will give our results and tell you a little bit about how we prove this. And finally, we will give some directions and open problems. Okay, let's start the background part. Complex theorists have developed a rich theory of hard problems and their reductions. For example, Cook, Levin, and Karp developed the theory of NP completeness, which shows that a lot of combinatorial problems are as hard as the class NP. However, the fundamental problem, which is NP versus P, has not been resolved after decades of efforts. We are really unknown about whether these problems are hard or they are just easy, but we don't know how to construct an algorithm. We are not clever enough. One of the most promising ways to resolve the PMP problem is through circuit complexity. We have known since Shannon in 1950s that if we count the number of functions and small-size circuits, we know that most functions are hard because there are a lot of functions but only a few small-size circuits. This means if we randomly pick a function, it's very likely that it requires large circuit complexity. However, the best known lower bounds are really poor. For example, against general circuits, we only know slightly non-trivial lower bound, which is 3.1n minus little o n. And against the De Morgan formula, we know cubic lower bound, but it's only polynomial lower bound. For superpolynomial lower bounds, we only know the NQP lower bound against ACC0 circuit, which is still a constant depth circuit. So our knowledge on the lower bounds are really poor. So to understand our failure in proving complexity lower bound, people have developed some informal barriers which show the incapability of certain techniques. For example, Baker, Gill, and Solovey developed the relativization barrier, which shows that relativized techniques such that diagonalization cannot prove P versus NP. And Rasparov and Redick developed the natural proof barrier, which shows under standard cryptographic assumptions, there is no natural proof of strong circuit lower bound. And the algebraization barrier shows that major open problems in complex theory requires non-algebraizing techniques. So all these informal barriers show certain techniques cannot be used to resolve the major open problems. However, these informal barriers are limited in scope and can be easily circumvented. For example, a recent line of work called Hardness Magnification shows an easy way to bypass all these lower bounds. We have known some lower bounds which are easy to prove, for example, the cubic lower bound against the Morgan formula. And we know that if you can slightly improve this lower bound, for example, to prove a n to the 3.1 lower bound against the Morgan formula, we know how to imply some major separations. For example, P is not equal to NP. And there is a very long lines of work on this topic. So this means that we can use a simple reduction to bypass the natural proof barrier. So natural proof barrier cannot tell us much about this new framework. So what's the next step? One way to continue the story is to take a closer look on the gap between the known lower bounds and the desired lower bounds for hardness magnification, so that we can propose new barriers, bypassing the new barriers and propose new barriers. And in this way, we can develop our understanding to how to prove the lower bounds and why we cannot prove it yet. But there is another direction which is also very interesting, which is maybe the complexity lower bounds is unprovable in some sense. We can probably develop a strong mathematical theory with solid logical foundation that contains known complex theory result and formally prove that NP versus P cannot be resolved under this theory. So this is a principled approach to resolve the unprovability of complexity lower bound. So this is today's topic, and our result is improving current known result on this line of work. So now let's talk about some basics about bounded arithmetic and previous results. Bounded arithmetic refers to the fragments of piano arithmetic that captures proofs that manipulate concepts from a given complexity classes. For example, Cook develops a theory called PV1, which formalizes polynomial time reasoning. And Bus developed a theory called SI2, where I goes from 0 to infinity, which corresponds to the levels of polynomial time hierarchy. And Warwick developed a theory called APC1, stands for approximate counting, that captures probabilistic polynomial time reasoning. There is a rich literature on bounded arithmetic, and it has formed a very solid logical foundation of a series that corresponds to complexity classes. The intended model for the bounded arithmetic is a standard model where plus, multiplications, and other polynomial time functions are interpreted in the normal way in the standard model. To define polynomial time computable functions in arithmetic, the standard approach is to use Cobham's machine-independent characterization of polynomial time computable functions. Cobham shows that polynomial time computable functions Fp is equivalent to the following set of functions obtained from the base functions by composition and limited recursion on notation. Here the base function includes constant functions, doubling plus 1, the projection function, and the following sharp function that gives you a polynomial growth on the length of the strings. The limited recursion on notation is defined as follows. We have a base function gx, and we have two functions h0 and h1, which defines the induction step for the case when the first bit of the induction variable is 1 and 0, and we have an upper bound which shows that it is limited. Since this gives a characterization of Fp, we can use the function symbols obtained above to define polynomial time computable functions. Formally, we define LPV by the language that contains the constant symbol 0, 1, a function symbol f for each function introduced above, and the predicate equals and less than and equals to define the sentences in first-order logic. In this work, we use the following theory TIPV. For each I larger or equal to 1, TIPV is the theory of all true for all sigma bi-1 sentences over the language LPV mentioned above. Here, true sentences means the sentences that are true over the standard model, and we will define for all sigma bi-1 sentences later. First, give some examples. When I is equal to 1, T1PV contains as axiom of all true universal sentences. And since Cook's PV1 is a universal theory, T1PV contains PV1 as a sub-theory, which means it is at least as strong as PV1. When I is equal to 3, T3PV contains all true for all sigma B2 sentences. These sentences are of the following form. It starts from a universal quantifier, followed by two blocks of quantifiers that are bounded. Here, bounded means that the variables are bounded by terms in this language. Similarly, for general I, TIPV contains for all sigma bi-1 sentences, which means that the sentences are starting from a universal quantifier followed by I-1 blocks of bounded quantifiers. Now let's discuss the strengths of the theory TIPV. We have known that T1PV is at least as strong as PV1, and actually it's a much stronger theory if we set I to be larger. For example, the Fermi-Little theorem, which is if a to the p is not equal to a mod p, then p is not a prime. This is the for all sigma b1 formula in LPV if you take a closer look of the quantifiers. So it is an axiom in T2PV. And another example is the Dulwick pigeonhole principle, which means that if there is a function that maps 2 to the n pigeons into slightly more holes, then there is an empty hole. It is formalized as the following sentence, which says that for all n and for all z, if there exists a y such that it is smaller than 1 plus 1 over n times 2 to the n, which is slightly larger than 2 to the n, then there is an x, which stands for a pigeon smaller than 2 to the n, such that the function maps x to y. Here, this z can be modeled as a non-uniformity, which means that the principle not only holds for uniform functions, but also for non-uniform functions. This is true for all sigma B2 sentence in LPV, so it's an axiom in T3PV. These two theorems can be shown in TIPV for larger I, but we have known that the Formalization theorem is not provable in PV unless factoring is easy. And this Warwick pigeonhole principle is not provable in PV under plausible assumptions. So this shows that TIPV is a stronger theory. In fact, we know that T1PV is equal to T2PV if and only if TFNP is equal to FP. So under plausible assumption, T2PV is strictly stronger than T1PV. So let's see the relationship between our theory and some standard theories. For example, the theory APC1 introduced by Warwick, which is used to formalize probabilistic methods and randomized algorithm, is defined as follows. It extends Cook's theory PV1 by the axiom of Warwick pigeonhole principle of f for every PV function f. The Warwick pigeonhole principle is just defined as above. And in this talk, we can, for simplicity, regard APC1 as T1PV plus a Warwick pigeonhole principle scheme. Since Warwick pigeonhole principle is provable in T3PV, we know that APC1 is a subtheory of T3PV. Now we discuss previous work on unprovability of complexity lower bound. Rasparov initiates the study of complexity lower bounds in bounded arithmetic, and after several years of exploration, Pick, built on a technique from Krajak, established conditional unprovability results in subseries of T1PV. Later, Pick and Sussman firstly show the unprovability of strong complexity lower bounds in T1PV and also in a fragment of APC1. Here, the fragment APC1 is a weak fragment, which means that their unprovability is unlikely to generalize to APC1 directly. Let's take a closer look to Pick and Sussman's result on unprovability in T1PV and APC1. Pick and Sussman considered strong complexity lower bound that separates NP from co-n size, which is co-non-deterministic circuit. Let's fix the polynomial time non-deterministic Turing machine M and consider the following for all sigma B2 sentence SM, stating that for every sufficiently large input length n, for every co-non-deterministic size of 2 to the n to the epsilon size, the machine M must disagree with D on at least 1% of the input in strings of length n. They show that this sentence SM is not provable in T1PV and in a certain fragment of APC1. The motivation of our research is to improve their unprovability result in two directions. First, can we obtain similar results for stronger series rather than T1PV and a weaker fragment of APC1? For example, let's consider the standard APC1 or even stronger series that corresponds to the polynomial time hierarchy. And secondly, we want to have a more natural formalization of this lower bound. If you take a closer look to their lower bound, you can see that they formalize the hard language M outside of the theory, and we want to make it a part of the sentence, which leads to a natural formalization, but will increase the quantifier complexity, leading to some technical hardness of proving unprovability. Okay, then it goes to our results. Our formalization of lower bound is a generalization of Pick and Sussman's results. We consider almost everywhere average case separation between pi I circuits versus sigma I circuits. For instance, we consider the following sentence. For all sufficiently large input lengths, there exists a function that is computable by pi 3 circuit, such that it is far from computable by every sigma 3 circuits of small size. Here, pi 3 and sigma 3 are generalization of the third level of polynomial time hierarchy. A pi I circuit is a deterministic Boolean circuit with m plus 1 variables, where say x equal to 1 if and only if for all z1 there exists a z2 such that cx z1 to zi equals to 1. Formally, we can define the following lower bound sentence: lower bound I s1, s2, and n0, which means for all sufficiently large n, there exists a circuit of pi I circuit of size s1, such that for every sigma I circuit of s2, there are distinct input strings x1 to xm, such that on every one of these input strings, C and D output different answers. Here, n in log means that the proof can manipulate the object of bit length 2 to the on, which gives more power to the proof. This is a good thing because it means the unprovability result is stronger. And this is also done in peak assessment results. Our result is the following. For every I larger or equal to 1 and any choice of parameters d delta and n0, TIPV cannot prove the sentence LBI over these parameters. Here, n to the d is the size of the pi I circuit, 2 to the n to the delta is the size of the sigma I circuit, 2 to the n over n is the average case error parameter, and n0 means we only consider strings with length larger than n0. And this is the lower bound says that pi I circuit of size n to the d cannot be computable by sigma I circuit of 2 to the n to the d, even if we consider approximation with 1 over n factor over large input length. So since we know that APC1 is a subtheory of T3PV, we know as a corollary that APC1 cannot prove the sentence LB3, which is the separation in the third level of polynomial time hierarchy. Now let's give a very brief introduction about our proof technique. We extend the approach employed by Pick and Sesnam, which builds on earlier work of Pick and Krajcik. The main challenge for us is to obtain unprovability from stronger theory TIPV and also consider larger quantifier complexity of the lower bound formalization. So let's suppose towards a contradiction that TIPV can prove the lower bound sentence and see what's going on. The key idea of our work and the previous work is that if there is a proof of complexity lower bound in bounded arithmetic, we can obtain a corresponding complexity upper bound. And if the lower bound and upper bound contradict each other, we can show the unprovability of the lower bound. We use the following toy example to illustrate that we can obtain upper bounds from constructive lower bounds. Let L be a language in NP and M be a non-deterministic algorithm for L. Suppose that the lower bound we prove is NP versus coincide poly. A constructive proof of the lower bound will yield a refilter Rm, such that given a co-non-deterministic circuit Cm of size poly M, which is supposed to solve this language L, it finds an input X of length M on which M and Cm differs, which means that it fails on this input X. The algorithm refilter should runs in time 2 to the on, which is polynomial in the bit length to describe the lower bound. We will obtain an upper bound that approximates Lnx in deterministic size 2 to the n to the delta using the refilter Rm as a sub-procedure where m equals to n to the delta. Our plan is to encode the computation of m on length n as a collection of co-non-deterministic circuits over input length m, so that we can analyze it using the refilter Rm on input length m. For an input of length n, we divide it into two parts as follows. For every string w, we define c to the w of n to the delta y as a circuit that simulates m on the concatenation of w and y, which is this circuit. By an averaging argument, we know that over a random w, there is a y star such that the refilter R given c to the w, it outputs y star with probability at least 2 to the minus n to the delta. This is because there are only 2 to the n to the delta different y to output. Recall that here m equals to n to the delta. Let's fix this y star. In order to compute mn x for x of length n, we first divide the input x into two parts, w and y, as described above. We will only care about the case where y equals to y star. If it is not true, we simply output a random bit so that it always outputs correctly with probability half. Concretely, given input x, which equals to w and y, we first run the refilter R on the circuit C to the W. If we don't get y star, the algorithm immediately outputs a random bit. Otherwise, since the refilter always reports a point on which the circuit differs from the language L, which means that m given y star is not equal to Cw given y, by the definition of the circuit C to the W, this means that m running on the string w y star, which equals to x, is a complement of m running on y star. Since y star is a fixed string, we can even hardwire the value m y star into the circuit, which further means that when r c to the w output y star, we can always output mx, which is m y star, correctly. This yields a circuit Bnx of size 2 to the n to the delta that can approximate the non-deterministic machine M with a 2 to the minus n to the delta advantage. This contradicts the original lower bound. Given the intuition from the toy example, let's take a closer look at the proof of reveal of the unprovability result here. Suppose towards a contradiction that the sentence lower bound I is provable in the theory TIPV. Since this represents an average case lower bound for pi I circuit versus sigma I circuit, it should imply a provability of a worst case lower bound for pi I circuit and sigma I circuit, which we denoted by this sentence LBI of worst case. From a proof of this worst case lower bound in the theory TIPV, we can extract an upper bound for every poly size pi I circuit EM, which means that every such circuit can be computable by a deterministic circuit Bm with an sigma p I-1 oracle gates of size 2 to the m to the little o1 with an advantage of 2 to the minus m little o1. And in the third step, we use the Hardness amplification result of Hadley, Vatten, and Viola in NP and extend it to polynomial time hierarchy. By this, we show that if every such pi I circuit EM admits such an approximation, every pi I circuit of size n to the d must agree with a sigma I circuit of size 2 to the n to the delta on at least 1 minus 1 over n fraction of the inputs. This is done by the Hardness amplification. And finally, if TIPV is sound, this is in contradiction to the provability of the lower bound sentence, which states an average case lower bound pi I circuits against sigma I circuits. The second step is a main lemma of our result, and it is a generalization of the toy example. Here is a comparison of the toy example and our main lemma. The goal of the toy example is to obtain the non-trivial upper bound that contradicts the original lower bound. And the algorithmic context we have is a refilter for NP not contained in coincide poly, and the input we feed to the refilter is a circuit CW defined above. And the goal of the main lemma is the same, and what we have is the provability of the sentence lower bound I in the theory TIPV. And what we do is to use some witnessing theorem to extract a winning strategy for some game where there are two players, the existential player and the universal players. This witnessing theorem is based on an earlier result of both Kuljic and Sipen. And what we feed to this winning strategy is a carefully chosen universal player that generalizes CW circuit. What we do is to replace this by some function designed based on the Nissan-Wigderson pseudo-random generator. Although we don't know how to interpret it in terms of pseudo-randomness, our proof crucially rely on the particular pseudo-random generator construction. In the end, we give some directions and open problems. The first open problem is, how should we interpret the unprovability of lower bound? Mostly we just believe it as a theorem that states that if you stick to some constructive method, which is characterized by the TIPV series, you cannot prove this lower bound. However, there is another interpretation, which I personally don't believe, is that this may be a hint that the upper bound is true, which means that the lower bound is actually false. This is possible because there are two ways for the unprovability to hold. First is that it cannot be proved, and secondly, it is because the lower bound is false. Of course, it cannot be proved. The second example is that, can we show that APC1 cannot prove strong compensated lower bound that's separating the second level of the polynomial time hierarchy? It seems that there is some redundancy if we move up to the third level, and we wonder whether we can reduce the result to the second level of the polynomial time hierarchy. And finally, can we establish the unprovability of worst-case complexity lower bound? And this may be a hard problem, but we don't have any evidence for the hardness yet. And that's all for today's talk, and thank you for listening.